Okay, so 11.8 introduces a new way, for the most part, of thinking about some of these graphs that we've been looking at. Much like when you were in pre-calculus and you were introduced to polar coordinates, okay? But polar makes life easy in general, right? So let's just kind of talk about the three different systems we have, all right? Currently, we have what we call a rectangular system. That's what we've been using. And if you were to graph a point with coordinates x, y, and z, you could think about that point being a corner of a rectangle, where if you sit it in the first octant, this would be points with coordinates x, y, and z. Okay. So that's one of the reasons we call it rectangular. We will be dealing with rectangular and cylindrical and spherical coordinates throughout the rest of the unit, or the rest of the year pretty much, until we hit DiffyQ. So make sure that you kind of follow along, and if you need help, please ask, because these are going to help when you get to integrating later on. Cylindrical looks something like this. So if you imagine a cylinder wrapped around or centered around the z-axis, and we put a point, let's say right here, instead of saying, go out x, right y, and up z, what we're going to say now is to start on the x-axis, and we're going to go out a certain radius. Okay? And then we're going to rotate so that we're underneath the point that we need to be. So now we're going to look something like this. And this angle here is going to be called theta, which isn't news to anybody, right? You're used to seeing theta with respect to the x-axis and polar anyway. And then once we go out a radius and rotate a certain number of degrees or radians, now we can say let's go upward until we arrive at our point. So then this would just be z. Okay? So our cylindrical system, our points will be defined as r comma theta, which is actually how you define polar, right? The only added component here is that you have a height attached to that. Okay, so that's what we mean by cylindrical.
So you don't have to worry about
It's exactly like polar, but now you're just either going up or down a certain amount. Does that make sense so far? Okay.
You don't have to worry about theta off different axes.
No, it's always defined with respect to x.
Like in the x, y plane.
Yes, in the xy plane with the positive x-axis, just like with polar. Okay. Spherical. So this is rectangular. This is cylindrical. Let's see if we can draw. So what I'm going to do is try my best to draw the part of the sphere that we need. It's a hemisphere, yes. Okay. So, I mean, if we want to draw the whole sphere, you know what? Let's do it.
That's a sphere, yeah.
That's a sphere. Use your imaginations.
I can't draw.
Okay.
That looks like a giraffe center.
Now, if you kind of followed what we did here, right? what did we do first? We went out a certain distance from the origin, right? And then we rotated. Well, we're going to do the same thing here. Okay, so you can imagine. Maybe we should define the points first. So any particular point in spherical coordinates is going to be defined by a radius rho, an angle theta, which is the same angle theta as before, and then a new angle phi, which we'll define in a minute. Okay? So what this means then, so if you imagine what we did first, go out a radius rho, and now theta means rotate, theta, rho. It's like a little pea with a little tail. Okay, so is everybody clear on what I've done so far? I've started from the origin. I've gone out a radius. We're calling it rho now. I've rotated the same theta that I've done, or that I did before in cylindrical. Okay, and now this phi is going to be with respect. So this is the angle with respect to the positive z-axis. Okay, so for instance, if I wanted to sit right here where I'm currently at, what angle would this make with positive z? 90, right? Because z is up here. So currently, if I wanted to end up right where I'm positioned, I would say I go out rho, I rotate theta, and my phi is actually going to remain 90 degrees. Does that make sense? Now, if I wanted to kind of go up towards the z-axis, then what would I do? Increase or decrease rho? Or phi? Decrease. If I made it 0, where would I land? Right on the z-axis. What if I made it greater than 90? You go downhill, right? So what is rho going to be between here? Or I keep saying rho. Phi. Phi will be between possibly 0 or 180. Okay? If you go more than one, we're not going to make it more than 180 because this will have unlimited. The theta will take care of that. You see what I'm saying?
What would be correct to have?
Explain what? Sure. So you start at the origin, you go out a radius rho, you rotate theta, just like we do in polar, and then now this last variable, phi, is defined as the angle. So let me actually draw this in. Let's say I rotated up here. So now this would be phi right here. This would still be theta, and then rho would be the distance from the center to the sphere on the surface there. Okay? So phi is always the angle with respect to the positive z-axis. Theta is always the angle with respect to positive x. And then rho is just telling you how far out along the sphere where you are, basically. Yes?
If it's a sphere, doesn't it not matter?
Does,
It still makes the same shape, doesn't it? Oh, it just lands on a different point on the sphere. Right?
yes. Yes. Yes.
Well, like, in polar, sometimes you see angles like 540 or something.
Yep.
Are we going to see theta or phi be over?
No, we're not going to make it that complicated. We're going to always assume theta is between 0 to 360 and then 0 to 180 for phi. Okay. We're not going to do the pre-calc thing where, we've rotated 80 times around. Now what quadrant are we in? Now this is going to be much more run-of-the-mill, What angle are we? 60 degrees. Okay, great. So where does that put, pretty basic stuff. All right? Okay. So does everybody kind of understand the setup for all? Obviously, rectangular makes sense. Cylindrical and spherical are okay so far? Okay. So before we make all the connections between all three, let's talk about some basic equations. and their graphs. This one we've already done, but in rectangular, if I do x equal to a constant, or y, or z, these are all what?
Plane.
They're all planes. Very good. Think two-dimensionally first. If you have x equals 5, that's a line, right? If we are in 3 dimensions, that becomes a plane. That's the easiest way to think about it. Now, in cylindrical, what we're going to do is examine the same kind of thing. So what if each one was just a constant? So if I had r equals a constant and nothing else. Think two-dimensionally, so if you have to think polar first,
Would it be like discs?
many,
Cylindrical plane.
Cylinders.
it's going to be a cylinder. Yeah, it's a bunch of discs stacked on top of each other, basically. Does that make sense? So if you think polar first, r equals 4, let's say, that's just a circle with radius 4, right? Centered at the pole. If we're doing a 3-dimensional graph, then we just extrude along the z-axis and it becomes a cylinder. That's the easiest way to think about it. Okay. Now theta equals, let's say, some constant. It's a plane. In fact, this is going to seem a little strange, but we're going to call it a half plane. Which I know makes no sense because planes extend indefinitely, but I think you'll understand. If I were to say, for example, theta equals pi over 4,
Oh, so like
you'd rotate over how much?
45.
45, right? And then you get this line, and then here's your plane, but the problem is that if I go back into the third quadrant, now theta is not
just
45 anymore, pi over 4. Does that make sense? So this plane gets cut off at the z-axis and then extends in that quadrant. Does that make sense? And now z equals a constant. Well, we already know what that is from before. This is just a plane. Still the same z as it would be in rectangular, so that's not going to change. Okay? Now in spherical, if I do a radius equal to a constant, now it's going to be a sphere. Another way to think about this, it's kind of like before. If we're in polar, it's a circle. If it's r equals a constant, in cylindrical, it's a cylinder. Here, if I have a radius, which is now rho, equal to a constant, it's going to be spherical, or it's going to be a sphere in spherical. Reason is, you can range theta and phi from any values that we've been talking about, so you're going to hit every octant possible when you go out this constant here. Okay. This remains the same. It's not a different theta. These are all, if you see any overlap in variables, they're the same in either coordinate system. But now let's talk about phi equal to a constant. Usually I do meter sticks right now, but I am recording the lesson. But what's that? It would be a cone. Okay, because if all you need to do is make sure that this, so here, this will make sense. Let's say this is phi here, right? And let's say that I'm right now exactly on the YZ plane. Well, couldn't you rotate around the z-axis and keep that phi the same exact angle? Okay, so that's where we get the cone shape from. Okay. And again, if I had the meter sticks, I would take it and spin it around, and everybody would understand. But can't really do that here.
So what was the equations were like at the beginning of the year when you said like if you have an equation with just do the variables instead of three, you just extend it along that third. Is that what we're doing?
Essentially, yes. Okay. All right. Now, here are the links that we need to get really familiar with really quickly. Conversions. So, let's say we are dealing with cylindrical and rectangular, and we want to go back and forth between these. So cylindrical. Actually, instead of an and, let me use this. So converting back and forth from cylindrical to rectangular. Okay. We already said that cylindrical was basically what? Again? Polar with an added z, right? So if you remember your polar equations, you're done. What does x equal in polar? Y equals, and z in rectangular is z in cylindrical. Now we also said that r was equal to the square root of x squared plus y squared, and occasionally if you were interested in the angle, I think tangent was usually the easiest way to do that, right? Tangent theta is y over x. So those are the conventional conversions from polar to rectangular. The only difference is that in cylindrical we have the added z component, but that doesn't change. It's still z. So there's not really anything to convert there. Okay. Now, what if we have spherical to cylindrical, or the other way around? Okay. So probably the easiest way to come up with these equations is to actually sketch a cylinder and then look at both ways of getting to that position that we're interested in. So here's my cylinder. And let's say we want to get here. And now let's just talk about all the different ways that we can get there. We can rotate theta, go out r, and then go up z. Does that make sense? Or if I go straight from origin to point, that could also be the radius in spherical, which we call rho. Does that make sense? And then, in addition, we have this phi that's made with respect to the positive z-axis. Okay, so those are all the variables that we need to figure out a good way to convert back and forth between these. And you know what? This will help when we start coming up with the relationships here. This angle here, phi, where is it in this right triangle? So it's also here, right? Alternate interior angles, if you will. And then now we can find a whole bunch of relationships. So for instance, the hypotenuse, rho, of this right triangle, do you guys see it? What are the legs? So that'd be the square root of r squared plus z squared. So there's one conversion. Z. So if I know the hypotenuse and I wanted to find z, here's the only angle in the triangle I have, right? This z would be adjacent to that angle. Does that make sense? So if you're using SOHCAHTOA, you can say cosine phi is equal to rho over z. So in other words, z would be rho cosine phi. You guys following that?
No, not really.
SOHCAHTOA tells us that the cosine of phi, so here's your right triangle. What's cosine? Adjacent over hypotenuse. So it's z over rho. All I've done is just move the rho over, so z is alone.
Why do you have like rho and r?
Well, because the radius that we've gone out in the xy plane is r, right? But if we're talking three-dimensionally along a sphere, when we go from center to point, that's a radius for the sphere now, so they're not the same radius. So we call that rho. Let's see, what else do we have here? R. R is opposite of phi, right? So we could say that R equals rho sine phi. It's weird getting used to all these new variables, right? Theta in cylindrical is theta in spherical, so there's no need to worry about that there. And let's, just like in polar, we had a relationship for tangent. If we use the right triangle in the picture there, what would tangent of phi be? R over z. Okay, so here's a set of equations that will help you link between spherical and cylindrical. Okay. Now, the good news is the hard part's over. The rest is just algebra. If we have the other combination, spherical to rectangular, or vice versa, so we want to maybe go back and forth between a rho, a theta, and a phi to an x, y, and z. If I want to know what x is, what we're essentially going to do is combine the formulas above. So what is x? Where is it? There it is. X is r cosine theta, right? But we also know that r in spherical is rho sine theta. So what we're going to say is, instead of r cosine theta, we're going to say x equals rho sine phi cosine theta. So all we're doing is substituting in r from the previous set of equations. Does that make sense? And we can do that with y. Normally y is r sine theta. But what's r? R is rho sine phi. Maybe I'll make that clear. So this part here is r, right? And then we still have what? Sine theta. Okay. Z, well, we already have z from before. Z was rho cosine phi. So that one's done already. Okay? Now, let's talk about rho. Rho was the square root of r squared plus z squared. So now we're going back the other way. Well, what's r squared? R is root of x squared plus y squared, so r squared will be, yep, So rho would be the square root of x squared plus y squared plus z squared. So just algebra here. Hopefully this isn't too confusing. Just plugging in the formulas. Let's see. Tangent of theta is still going to be y over x. That's not any different. But if I want to talk about the other angle phi, we have a cosine relationship. I kind of have it here. That's how we found the equation for z, right? Cosine phi is z over rho. So if I want to write cosine phi in terms of rectangular, z is good, but what's rho? Yep. Okay. Now you have everything you need to be able to go back and forth from rectangular coordinates to spherical to cylindrical and vice versa. All right, so we'll just do a couple of quick examples and then we're done. Okay, so for this one, let's say we wanted to find the rectangular coordinates and we were given an r, a theta, and a z. So what mode is this? Cylindrical. So, and we have 4, 5 pi over 6, and 3. And then we'll also do one where we know a rho, a theta, and a phi. And let's say those coordinates are 4 pi over 3 and pi over 4. Okay. How do we convert to rectangular if I know r, theta, and z? Z stays the same. So z is 3. What about x? So 4 cosine of 5 pi over 6. That's quadrant 2. That's negative root 3 over 2, right? So negative 2 root 3. And then y is just r sine theta. Quadrant 2 sine's positive, so that'll be 4 times a half, which is 2. So your answer would be x, which is negative 2 root 3, y, which is 2, and then z stays 3. Okay, in spherical, what's x? Rho sine phi cosine theta. So let's just plug everything in. Rho is 4 sine of phi, which is pi over 4, and then cosine theta, which is pi over 3. Sine of pi over 4 is root 2 over 2. Cosine of pi over 3 is a half. So that's going to be just root 2. Y is done similarly. Y is rho sine phi sine theta. I know I'm going kind of quickly, but you guys will get there once you start going through the homework. Rho is just 4 sine pi over 4. Bless you. Sine pi over 3. So 4 times root 2 over 2, sine of pi over 3 is root 3 over 2. So this is just root 6. And now z was just rho cosine phi. So that one's easy. Rho is 4 cosine of phi. Phi was pi over 4. whoops, I don't know why I wrote 2. So 4 times root 2 over 2 is 2 root 2. Well, you'll remember them in time. Remember, I'm giving you those 3 extra days, right? We're not quite done yet. Hold on. So coordinates root 2, root 6, 2 root 2. Okay, so those are just straight up, here are some points. I think you guys can handle that. Let's talk about some actual equations now. So equations. Let's say I have the rectangular equation z squared equals x squared plus y squared. Let's go ahead and find one in both cylindrical and spherical. Well, in cylindrical, do we want z's? Yes. Do we want x squareds and y squareds? Do we know what x squareds and y squareds become? Or just go straight to r squared? You could do r cosine theta, r sine theta, and then you pull out the r squared, and then you get cosine squared plus sine squared is 1. Or just go here. So z is r. In spherical, we don't want z's, x's, or y's. So let's see. Z squared. Actually, why don't we take this? Since we already have z equals r, that might be easier to handle than going all the way back to the beginning, right? What's z? Rho cosine phi. And then r. Well, in spherical, we don't want r. So go back to the spherical. Rho sine phi, right? So if we simplify this as much as we can, we could say 1 is equal to tangent phi. But what does that give us for phi then? Pi over 4. So now, look. This, from the get-go, you should have known from yesterday is what shape? It's a cone, right? What's this the equation for? Another cone. So now you're starting to see them kind of come through and how they link back and forth. I guess here, if you wanted to, you could do both. If you wanted to be real technical about it, what would this be? 5 pi over 4. But phi does not go larger than 180. So maybe we just do plus or minus, because that would be the equation, right? So then, I mean, 3 pi over 4 would be the other answer. But see, it's kind of strange here because tangent of 3 pi over 4 isn't 1. But anyway, one more. So this is rectangular and cylindrical. This is just z equals. In spherical, usually once you have the cylindrical, it's easier to deal with the cylindrical than it is to go back and start with rectangular. Z is rho cosine phi. R was rho sine phi, so we're going to make it rho squared sine squared phi. So if you get rho on the right, you get cosine phi. Oh, you mean up. Sorry about that. Cosine phi, if we're dividing by sine squared, that's the same as cosecant squared. So this would be fine. Oh, don't be afraid of a little cosecant.